Hello everyone, this video is about radiation intensity and directivity of a finite dipole antenna. In one of the previous videos, we have already covered the basic of a finite dipole antenna. And we also know that the radiation patterns is given by E of x and then J I know. And then so the electric field from the radiation patterns basically contains two parts. We have this part which determines the direction of the antenna, and this is so-called array factor. And this part here is responsible for the element, the magnitude of the elements. So this is the element factor. And today, what we are looking for is the radiation intensity and the directivity. And to be able to get the directivity, we need to find out the radiation intensity. And all we need is to manipulate this formula. So to begin with, let's revise what we have learned. And we have learned some while ago, we have already learned the power density, the power density of the radiation field. Alpha is power density. It is given by S stands for the protein vectors. Yeah, the alpha is the protein vectors. Is given by the magnitude of E theta square and then divided by 2 eta. Yeah, eta is the characteristic impedance of air. Characteristic impedance of the medium. And now, what is the magnitude square according to the equations here? First of all, this is just a complex number, and the magnitude of it should be 1. So, in other words, if we are going to find the magnitude only, we don't, we need to take care of this as well, but um, we just need to find a square of this one. So by direct observation, we have this y, yeah, the square, I naught square, and this term will vanish, and divided by 4 pi square r square. And finally, right, we just need to take the square of this term. Now that's good. If we can find the power density, there shouldn't be any problem of finding the radiation intensity. The radiation intensity is given by the alpha H power density times r squared. So if we continue, what we need to do is, right, need to write down what the radiation intensity, U. U is given by R squared, and then SAV. And by direct observation, we have this term here, all we need is just to just copy, right? 4 pi square. By the way, I make a mistake here, yeah? Divided by 2. 2, I forgot to do that. So this should be divided by 2 eta. 2 eta. Yeah. So based on what we have got here, we need to just do a simplification on the fly. Yeah, 2 eta 4 pi square and r square. So we just do this 8 eta. And then we cancel out this term. So 8 pi square. So this is the result from direct inspection. And we also need to make use of this formula to calculate the intensity. We just do r squared times this one. So if we do that, then what we have left here is the denominator become 8 pi squared, and then we just copy as cos. Now, this is the formula for the general finite dipole antenna. In order to get the, in order to calculate the directivity, you need to find the total radiated power based on the radiation intensity. But However, the formula here is very complicated. If you square this term, you end up with a chunks of expression. Fortunately, uh, when you look at this term, finite dipole antenna, there is a certain class of dipole antenna which uh, where we can further simplify the expression and we can calculate the directivity easily. And this is so-called halfway dipole. Halfway dipole. So what I am going to do is, right, I am going uh, to preserve this formula, yeah, these two formula. And the next thing that I'm going to do is to find out the halfway dipole. Yeah. So from now on, the title here is going to change. Uh, what we are going to do is to find out the radiation intensity and the activity of a halfway dipole. Uh, and this is going to happen when L is equal to lambda divided by 2. So this is the situation, the special case that we are looking at. And the antenna with the length exactly equal to half wavelength is so-called halfway dipole. And this is what we are looking at. So what are they? They are the finite dipole antenna with the length being equal to half of the wavelength. So I just need to write down here, yeah. Write down here, yeah. L equals to lambda divided by 2. Now you can read the write more easily. Yeah, just good enough. So according to the expression here, the electric field from the radiation pattern will become yeah, we can do that. We can find out by substituting L being equal to lambda divided by 2. If we do that, then this term will go because the value inside is going to be pi divided by 2. So this one go. And this one will become pi divided by 2. So this is what you are going to get here. And the array vector becomes much simpler. And how about the L-phase power density? The L-phase power density is again similar, with an exception here. We don't have this term anymore. So we cross this out, and then we have this one here. And do not forget that we don't use KL anymore. So this will become the alpha power density. So I better relocate this because we are running out of space. Pi square r square, and then cos sine theta square. So this is what we have achieved. And this is the characteristic of half-wave dipole. And how about the radiation intensity? According to what you have got here, uh, you just need to cancel off this term. And now actually you can just directly, you can just get the radiation intensity by direct inspection. So U becomes R square S AV. And now, because the array factor become much simpler, you can actually calculate the total radiated power based uh, on the array factor. So this is something that we can do here. So if you do that, you just integrate U with the total solid angle. So if I'm going to expand this expression, it will become 0 pi, 0 to pi, and then U, and then sine theta d phi. And if we substitute the expression of U into this one here, then we will get 2 pi 0 d. I'm going to simplify this on the fly. Pi, and then this trunk of expression. Yeah, we have a log of constant independent of the angle. And d theta. And fortunately, you don't have to go through a lot of calculation. Somebody has already done this for us. So what we have left here, if you do it very carefully, right, this one becomes 2 pi, and this one, we can just copy it across. And 8 pi square. And how about this one? And somebody has already done the calculation here for this integral. The value of this integral is 1.217. So this is very good news. So what is this term? Integrate U uh, over the total solid angle, and this is so-called the total radiated power. And this is what you are going to get. And now, and how about the directivity? And do not forget that the formula for the directivity is 4 pi U divided by power rate. And we have already got the expression for U. For pi, and then you just copy the expression here. And the bottom one is just as simple as the top one. We have 2 pi here, and then we have 8 pi again. And then you have 1.217. And if you do it carefully, all what you will end up with here. Remember, when you have both the top and bottom have this term, they can cancel out with each other. So eventually, what you have here is 1.642, and then this expression. So this is the directivity of your half-wave dipole. And what is left here is the maximum power, the maximum directivity. We can calculate this. The maximum directivity when this, so first of all, consider this factor. This factor is cosine square over sine square, something like this. The maximum value of the top one is 1, and for the lower one, the maximum value is also 1. I'm not sure whether we will have something larger than 1. Apparently not. Apparently not. So we can just say the maximum directivity is equal to 1.642, and this happens when pi over 2 cos theta being equal to 0. And if this is the case, or beta equal to pi over 2. So when the angle is at right angle, the so-called end-fire antenna, then the radiation pattern. So if you have a radiation field where V where theta is equal to 0, yeah. Then if you do that, and then you work out the radiation field. This one is 90 degrees. And according to what you have here, the maximum radiation is going to happen when theta is 90 degrees, pi over 2, or this angle. So what you have is this kind of radiation field. Now here you get the maximum directivity. The antenna will be pointing to the z-axis. Remember that, right? The z-axis. So this is going to be your antenna. Okay. If you have any question, please leave your questions to the comments box. And if we have time, we will try to answer your question. Thank you very much for your attending these video lectures. I hope it is clear enough to you. Thank you.